My name is Mariusz Postal and I am representing the Institute of Information Technology, Technical University of Łódź. It is my pleasure to present my research work related to object-oriented Internet, focusing on reactive interoperability. To keep your attention, let me present the agenda for my presentation. At the very beginning, let's describe the scope of my research. Talking about machine-to-machine communication, I will try to point out the most important, in my opinion, features of this application domain. Because the Industry 4th generation, IoT and in general cyber-physical developed, based on the machine-to-machine communication, may bother with the problems related to traffic asymmetry, data holder mobility, multi-vendor environment. I will investigate the possibility to engage the reactive communication instead of interactive communication. To make my proposals adaptable by the end users, I will propose details making the presented abstract model a foundation for further development. To check out the full story, find the article using Google search and enter the phrase Postal Reactive Interoperability Sprinter link. The article is also available on the ResearchGate. As I said, the machine-to-machine communication is a foundation for the cyber-physical system, Industry 4.0 solutions, and Internet of Things discipline. In the case of cyber-physical systems, a variety of entities may be aggregated into distributed information processing solutions. In this case, we are opening the public connectivity domain, which requires the Internet as a globally scoped communication infrastructure. Parties interconnected over any network require special precautions that must be taken against malicious users to assure the best possible level of security. To address this security demand, suitable protection methods may be applied to network traffic and data transfer objects. For network traffic, it is accomplished using intermediary devices to enforce traffic selective availability, based on security rules, against unauthorized access. For the data transfer object, simplifying data on the wire, it is accomplished using cipher algorithms against bit streams, formatted as a message traversing the network and containing processed data. The integration of a cyber-physical system using multi-vendor products requires that machine-to-machine communication must employ international standards as the interoperability foundation. To address the industry requirements, we need meaningful communication, without programming. This feature is coined as plug and produce. Machine-to-machine communication requires information exchange technology. In practice, the information must be represented as bit streams, called data. To make this representation useful, in the context of information processing, there must be defined semantic and syntax rules, called semantic context. The syntax is used to validate the correctness of the bit stream, and the semantics rules associate meaning to the correct bit streams. As I said previously, we need a security context to make the communication robust against malicious network users while using public infrastructure like the Internet. Let me shortly present a typical domain model, describing the most important features of the mobile applications, compliant with the more general IoT concept. We need it, as a foundation for a further discussion, addressing systematic design, development, and deployment methods and tools. A detailed description of this model is covered by my previous publications. A starting point for further discussion is a generic architecture of the machine-to-machine interoperability presented on the screen. There are no options. To establish interoperability between two dispersed parts, we may use session-oriented or session-less communication patterns. On the left, we can see the session-oriented client-server model. This is a data exchange scenario that requires establishing, in advance, a session relationship before any processed data can be sent over the wire. In this case, the connection-oriented services set up a virtual link, making a tight relationship between the communicating parties. The session is responsible for retaining state information about each communicating party for the duration of multiple requests. In this scenario, to establish a new session, the client must send an originating request, connect, over the network to the server exposing relevant data. Sometimes, it may be difficult, or even impossible because of network traffic asymmetry, and data holder mobility. The session-less archetype is a message distribution scenario, where senders of messages, called publishers, Do not send them directly to specific receivers, called subscribers, but instead, categorize the published messages into topics without knowledge about which subscribers, if any, there may be. Similarly, subscribers express interest in one or more topics, and only receive messages that are of interest, without knowledge about which publishers, if any, there are. In this scenario, the publishers and subscribers are loosely coupled by distribution channel. Distribution channel is responsible for filtering, buffering, and routing the messages to pre-selected delivery points. Let me stress, the publishers and subscribers are decoupled in time, space, and synchronization. It is essential that the proposed architecture has no single point where human interaction is possible, in compliance with the requirements of the machine-to-machine communication concept. In my previous publication, I proposed a recommendation on how the OPC Unified Architecture International Standard may be mapped partially on this architecture, to satisfy multi-vendor environment requirements. This discussion can be concluded that only reactive interoperability can be used to overcome network traffic asymmetry and data holder mobility. Therefore, the further work is concentrated on this communication scenario. Still, the reusability of the existing concepts and solutions must be concerned. To make two parties interoperable, both must use the same semantic context to assign the meaning to bit streams exchanged over the wire. In general, the semantic context may be agreed against at runtime or design time, but always in advance. According to the proposed model, this process is supported by the address space management, and information model concepts, which may be partially implemented in compliance with the OPC UA standard. The runtime approach is straightforward after establishing the session, because the session is a tight relationship that can be used to exchange appropriate metadata. In the context of the metadata exposed by the mentioned entities, the client can select what data it is interested in. Because there is no similar tight relationship between the subscriber and publisher, the subscriber must deal with this issue in a reactive, rather than proactive way. Let's see how to design and implement a reactive interoperability archetype. As I pointed out previously, the subscriber must deal with data exchange and establishing a semantic context coupled with security context in a reactive rather than a proactive way. It explains the name. From the previous diagram, we can abstract the reactive interoperability model, where we have common functionality, namely a part responsible to get access to process data. Here is also the configuration component and security management functionality. The publisher and subscriber are derived from a generic reactive application class. They depend on a common distribution channel used to transfer messages from place to place. It is worth stressing that in this scenario, it is impossible to establish a semantic context based on a session. It is not indicated on the screen, but I propose to use types defined by the custom information model as a foundation for the semantic data concept. The same approach can be used to establish a security context. Let me stress, in my proposal, type of transferred data is a principle to construct meaningful and secure data transfer objects, encapsulated by exchanged messages. It is just a theory, a set of assumptions, that now we can use to propose a concrete implementation meeting the community expectation. I believe that a detailed description of the implementation is not relevant to us, in contrast to an analysis of how to use the proposed domain model to make strategic design decisions and functionality distribution. From the above discussion, we can learn that the main design decisions must concern reusability. It means using the same part in many scenarios, flexibility, interoperability in the multi-vendor environment, and last but not least, deployment without programming. To meet these requirements, the mentioned on the screen design patterns have been used. Separation of concerns, to allow independent development of the parts. Dependency injection, to allow late binding of independently implemented parts. Adaptive programming to improve the adaptability of the program against the production environment changes. It is used at the development and deployment stage. Piece-by-piece integration of a cyber-physical system, using multi-vendor products, requires that machine-to-machine communication employs international standards as the interoperability foundation. Following the presented conclusions, OPC Unified Architecture Part 14 Pub Sub is selected, in this respect. By design, This standard should support the required publisher-subscriber communication pattern, but it covers only partially the requirements of the applications concerned. Therefore, my proposals shall be recognized as far beyond the specification scope, although they are still compliant with the standard. Let me recall, I propose to use type definitions as the principle to establish semantic and security context. It means reusability of the information model concept used by the session-oriented counterpart. It is the implementation architecture I propose. Let's look at selected building blocks. The main part is a development kit, SDK, available as the NuGet package. To promote the polymorphic approach, it has the factory class data management setup, that is a placeholder to gather all injection points, used to compose external parts. To be injected, the parts must be compliant, with appropriate contracts expressed as the interfaces. So, we have 4 interfaces, and it is expected that the functionality implementation represented by these interfaces is provided as external composable parts. The library and related work you can check out from GitHub. On GitHub, you can also find an ebook covering the topic in concern. In the public domain, on my account, there are also other supporting projects relevant for planned work and practical deployment of the presented solutions. The results, presented in the article, prove that the composite nature of the disciplines concerned can be relaxed by the composite nature of the running programs and postponing binding of the parts up to the system deployment stage. It also improves flexibility and adaptability of the existing solutions against any modification of the production environment, including but not limited to the selected interoperability standard change. Future work will be focused on machine-to-sensors connectivity based on the process observer concept. By design, it allows access to plant floor devices using a variety of field bus industrial network protocols. The next research direction is the usage of the data transfer object to control the communication behavior using the attributes attached. I am also going to investigate out-of-band communication to be used as a foundation for semantic and security context maintenance at runtime. That's all for now. Thank you very much for your attention. Contact me by email, in any case, questions or proposals you may have.